Okay, so I guess we can continue Abhishek's mini course on fluctuating hydrodynamics. So, Abhishek.
Okay, so resume this. So last time we were discussing non-linear fluctuating dynamics for dynamic states. And we said that there are three complex quantities which are spreads, and energy, and then we had Euler equations which look like the Euler currents were given by and these currents are of course expressed in terms of the electric fields. So this equation is a function of so then the idea is we expanded this currents to linear order in the fields, and so at the lowest level what we got is and then we looked at fluctuations of the field about equilibrium. So this equations were U alpha is at the lowest order, which has the form of system. Where this A alpha, which are so in this particular case, we can see that given that the currents are this, so let me just write the form of the event sheets. So from here one can see that if I take derivative with respect to R, the first one is this. Okay, so from this form of the Euler currents and the definition of the one can see immediately that this is linear order expansion. Okay, and then what we said is that from here one diagonalizes this matrix, and one finds that there are super diagonalities. Then rectangular different transformations. eigenvalues which correspond to the sound modes. So there are two left mode and right mode in sound modes, and there's heat mode which stays the same. Okay, so at this level, if you look at the correlations, then they are just delta function peaks. And then what we said is that we add so this is Euler, and then we add the Navier-Stokes corrections purely phenomenologically at this moment. So this is so these are always derivatives in the fields within the and then some nice terms. And this G and B satisfies some fluctuation discussion. Okay, so with this, what one thing is that at long term, all the fields have diffusive spreading. So the heat mode is and the sound mode. This is the peaks which travel with speed C and minus C. Okay, and then so these are so we are interested in correlations. Space-time correlations in the first field. And so this is like if I plot let's say any of these correlations, it will have these three peaks which are all diffusive. So and then what I said is that what we want to understand is if we now look at higher order corrections to the Euler current, then what are the changes in this correlation? Okay, so then the next procedure in the formalism is to write higher order terms in the Euler function. So this is the and so this will call it and these are objects that one can just from the equation of state we know exactly how to compute this. So actually, Mehan asked a question like, what happens if we have next neighbor interactions? So I mean, all this goes through. I mean, so all these steps are will be exactly be true. What becomes difficult is that for the nearest neighbor case, the partition function is it just becomes product form, and so I mean the calculation of this all these matrices A and H they just involve like simple integrals. Okay, so the computations are very easy to do. If you have next nearest neighbor, I mean, in principle, everything goes through, but all this, the calculation of this has to be done from numerical simulations. Like, so these involve all equilibrium correlation functions, right? Because they are like derivatives of the pressure. So there are some response functions and they can be related to equilibrium correlation functions. And for the nearest neighbor case, these are much easier to compute. But if you have next nearest or even long range interactions, this can you just have to do them from simulation. Yeah.
So last time you said the sound modes had KPZ state.
Yeah. So that's
So where exactly does that come from?
that's going to come from the nonlinearity. So now once I include the nonlinearity, we are going to see KPZ. That's what I'm now going to explain. Right. So now we include this term, and so here we get some additional terms. Okay, so let's say we now write these equations with the nonlinear terms, and again, we again now make this transformation from this fields, the basic fields U to so we apply this transformation R which diagonalizes A, So, so we define RU as, fine. Okay, so, so now we have these three fields and we use, indices with the five, R, A, alpha, so this indices indicate the normal mode, fields. So they're just some linear combination of the original fields. Okay, so now, so at linear order, I mean, these fields are decoupled, and we get equations like D phi A equals to minus del x of minus 16 A phi A, and then there's this diffusion and. And I'm just not writing it into matrix, so I'm just writing it. So these are the diffusion and noise. But at this level now, since I diagonalized this A matrix, so these fields are decoupled. Okay, so now if I use the same transformation after adding nonlinearity, then you can see that what I would get essentially is a new term which looks like, let's say, G A B C phi B phi C. But this is okay. So okay, so now and this G is of course related to this matrix A H, and it will also involve this transformation matrix with R. Okay, so okay, so now basically we have to analyze these equations and say what like what we can say about the correlation functions that follow from these equations. Okay, so now
so is it obvious that what would diagonalize the use for the matrix A will also diagonalize G, the matrix, the dissipation and the noise?
no, so this is not diagonal. Sorry, I'm just writing it. So I didn't put any. It's not diagonal, right?
So in general, they will be terms.
Yeah. So these are still matrices. I mean, after applying R, right? Yeah. Right. So I didn't put any indices. That's why I'm just writing it schematically. But these are all matrices. Right?
Are there some symmetries that we can already say? Something about G.
Yeah, so G has satisfies like in general, at least for the let's say for the active chain, you can do some symmetries in the so okay, but I'll write some of the important elements of this matrix. Yeah.
So that the term that was there in the equation had a B alpha beta times beta. That is somehow absorbed in the.
Sorry, say again.
That term.
This one.
Yeah.
Oh, this is there. Sorry. And for last time what I did was I was putting filters here, and this clearly after the R transformation, right? So they get.
Yeah, maybe just need it right in this. I think.
Yes, yeah. Right. So now, yeah. So now, so now in the parameters in my model are okay. So there's the pressure and the temperature, right? These are the main two main parameters that control everything. And so in the general case, let's say we're looking at pressure not equal to 0. In that case, what one can show is that this matrices have the property that G1, okay, so G it's A equal to plus minus 1 are the sound modes, right? And zero is the frequency. Okay, so if I look at the matrix corresponding to the sound mode, so each of these modes has a matrix, and if I look at the matrix elements in this case, so it has this property of G11 equal to G minus one, minus one, so this is non-zero. And, G zero, zero, and okay, so there are other symmetry properties, but I won't write all of them. And there's a lot of symmetry relations between this. But so these are some of the important ones. Now, okay, so now if I just look at the equation for the okay, so in general, this of course it's difficult to solve these equations. So one approach is just to do, do mode coupling theory and try to get some predictions. So that has been done, but so I won't go through the full analysis, but just indicate the rough idea of like how you see KPC from this equation. So let's say I put A equal to +1, and then what the equation I get is that T by 1 is equal to minus 12. And then I have a term, so it's important that there is a self-coupling. So this term is non-zero. And of course, then it also couples with there are other terms where it's G1 might couple to this is non-zero. So I will say something like 5 by -1 and so on. And then there are this diffusion terms, right? So okay, so now what I know is that I mean so these fields are traveling at speed 1 and -1. So I mean the interactions between these are kind of much weaker than like this term. So if I just drop this term, then one basically has the KPZ equation. Right? So then I can immediately I expect that this should essentially that phi 1 conditions. So then the prediction is that we should satisfy and I mean, so then this is like it's a complete prediction that say KPZ function is known exactly, and then the only unknown parameter is this lambda, which depends on this G11, and this is also known exactly from the microscopics. Okay. So from the microscopics, I know everything. I have a complete prediction for the correlation function. So yeah,
Very Galileo transformation, maybe the first they'll find the next term.
it's there. It is there.
But he's getting confident.
Oh, sorry. Okay, so therefore, if now one sees that the phi1 correlation, this sound peak correlation will be KPZ. So that's the.
What about the noise?
The noise, I mean, okay, so it's a matrix, but I mean, finally, actually the final results, whatever you put here, as long as there's some basic symmetry properties are satisfied, the final at long times the strength of the noise, everything just goes away.
I'm more worried that it's in. Right.
Sorry?
D by dx.
Yeah.
The noise.
Yeah.
Does that not change the No, I think it's basically five like age being behind.
Oh, yeah. Sorry, yeah.
More like the burgers.
This is like the burgers equation. So you have to map it of course, like this. Okay, so this is what one finds for the sound mode. So, so this is. And now, then we write the equations for the heat mode. And there we see that there is no self-coupling, right? So there's no self-coupling term. And in this case, the equation is so there's no so it doesn't move. So we just have we don't have a self term, and the leading term which is important is comes from this. This one is 30 11 suppose straight. And then there's okay. So now this again one can't solve it completely analytically, but you can at least get its scaling form correctly. And yeah, in the large x large time limit, you can sort of predict how, given that phi 1 has KPZ correlations, you can make like find the predictions for phi naught correlation. Okay, so in this case, what one the prediction is that phi is 0. So it has the scaling. Sorry. So this is the 3/5 exponent, and then the scaling function is the Rayleigh distribution. Okay, so this simply means that in Fourier space, it looks like e to the power minus a naught to the power 5 into e. Okay, so yeah, so finally, this is the main outcome of the this entire formalism that for the generic case where the pressure is not equal to 0, the fact that the G matrix has this form leads us to this form of the this KPZ correlations for the heat peaks and for the sound peaks, and this for the heat peak it's given by this.
What is the lambda? You scaling from the rising.
And I should put a sound, and then this is for heat. So this is scaling parameter which can be computed from this from the values of the geometry. So these values are also given exactly. I mean, there's
first time you scaling from everything.
Yeah.
You remove the asymptotics of
The large x. I think it's equal to minus x cubed. So I'll show after maybe in the next lecture I'll show plots of like how will it compare.
You know, this depended on ignoring this G1 minus 1 term. You know, that
Right,
these terms. So is there some physical reason?
So that yeah, so physical reason I said was like, see, these two modes are very they are moving in the opposite direction. Right? So you expect the interactions to be really small.
Okay, so essentially some kind of local, some kind of saying that you have local interactions and somehow things are hard with each other.
Right. Yeah. So I mean, this would be much more important than that.
Okay, and so can you estimate, for example, what the
no, so I mean, like these equations have been more like carefully analyzed using this mode coupling theory, where you keep everything and then just look at, and finally the predictions are okay. And then you compare the predictions from mode coupling theory with, let's say this, and it's found to be very close to.
Numerically, how small this term is?
Which term?
So this
So the effect of this, no, just this, no.
it's possible with in numerical simulation.
No,
It's compared to other.
okay, but then you would have to simulate really the hydrodynamic equations, keeping this and trying to simulate it. Right? That's the, I mean, so normally when one compares, one just does microscopic molecular dynamic simulations. And where you don't have a G, I mean, you don't have anything. Right?
Just have everything. It's all.
Yeah, it's all microscopic.
What can calculate G?
Yeah, you can calculate this G. Oh, you're saying the number may not be small. No, no, this is not small. I mean, even this may not be small,
No, including 5.
including this.
Yeah.
But then to see whether it has an effect, you really need to solve this equation numerically.
Ultimately,
Otherwise, yeah.
we compute the profiles numerically and then compute these terms too.
Yeah.
Numerically.
Yeah, I mean, see, at short times when they're kind of overlapping, of course, this will be important.
Yeah, that's what we expect.
Yeah,
Maybe it can be confirmed in numerical simulation.
but then you would have to simulate this equation.
But we can calculate 5 microscopic model by using the definition of the field.
Oh, okay, from the definition from. So this can be, okay, okay, right, yeah, then,
I would
yeah,
just be curious.
okay, yeah, we want to put it in pencil, but yeah, yeah, not.
So the overlapping thing,
Yeah.
see these 5 1s and 5 - 1, these are very extended fluctuating functions, right? So it's not like there are two peaks
Yeah,
which are
right, yeah.
separate. So strictly speaking, this overlapping, I'm not so sure.
No, but see, typically if you have,
If
you
you
have
have like two-
fluctuations, and the fluctuations will.
But the
kind of
typically
parallel.
is, vertical then-
5 1 5 - 1 to calculate the connected part of the correlation function that only goes down.
Right, yeah,
Some power of G and.
much faster than the other. code, yeah. So, yeah. Yeah, in fact, yeah, if
If you
you,
can go to substitute this back and apostolate, oh no, but you don't
Yeah.
have information about 5 1 5 - 1 correlation, right?
right, yeah, so numerically you can see, for example, if you do pi one xt, and pi, minus one xt, 0, then these are like almost zero, there's no correlation at all.
So this equation, because we describe the level of the original SPL.
Yeah. Right, yeah.
From alpha, the alpha.
Right.
Where the element goes after the.
Right, okay, so, so all those information goes into this G matrices. Okay, and one particular case is, okay, so, so this I said is the generic case. One special case is T equal to 0 and let's say alpha is 0. And beta is still finite. So this is event potential. And in this case, the this becomes different. Okay, so in this case, so this actually vanishes, and so then then in that case, what from here what we see is that since this is not there, and this we said it's not important. So in this case, the prediction is that the sound mode should just be diffused, stay diffused. Right, yeah. So there, I mean, so the alpha beta goes into determining this matrix elements, and that tells us whether it's going to have different behavior.
And I have a related question. I mean, by tuning these parameters alpha beta,
Yeah.
is it possible that some values that you can say the lambda of and get tables?
Okay, no, so see in this case, like for this value, I mean, then you do get it because then it becomes diffusive, the sound is because I mean this vanishes, right? So then you do get, I mean, this is 0 for this different parameters.
But then you get it into 1/4 there or the half.
No, you just get diffusive. Yeah, it's yeah. That is it would be. Okay, and but now the so for that other, I mean, so the special case this to whenever V is even potential. So in that case, the prediction is that the sound correlations it's a QB. And I mean, so. And the heat thing is still, this term is still there. So this is the. So it's again a levy, but with a different exponent. So here this corresponds to in serious cases 0 minus 3 minus 3. And there's some. Right, yeah. And maybe I should say that. No, right. Here there's no, in this case, there's no KPZ at all. Even though the exponent looks like.
Python is can you relate?
Oh, okay, sorry, yeah, that is, I mean, so, here, of course, we know that heat, like, for example, this energy correlation, which is one of the, things which gives this divergence in conductivity. So this again, you can compute using this, all of this, and there, this is 3/5 in fact leads to, 1/2 or 2/3 for the. For the heat current correlation.
But there's no scaling relation between the exponent. 5/3 and.
Oh, this and this, okay, sorry. No, yeah, there is. Yeah, I don't really know, there is a relation.
So 1 + 1 was.
Yeah, something like that, right, exactly. Which is satisfied in both cases.
So just a naive question, is there something restricted on the sign of these G11s? G1
This one.
Yeah, are they always positive or there is some or negative, or is there any some restriction on that?
Not.
But how does that affect when you do because that somehow determines your KBZ equation, so.
And the KPC, I guess the sign probably. I mean, like the case, I know it's always positive.
Okay.
But
Is there a reason why you say there's no reason if our line should always be positive?
at least right now I can't think of. Yeah, I have to think maybe there is a. Just like.
There is no property from 5, 0 to 5 1.
5, 0 to, so this is the coupling between, you're saying.
There's the equation that you have has nothing to do from 5, 0.
Yeah, this one doesn't have a between 1.
So 5, 0 is completely slave to 5, 1, 5, 5 minus 1.
Like 1, 0. Sounds like this. I think this is not there. But okay, this is I check and.
I mean, in terms doesn't involve any 5.
No, these are
It's just a diagonal.
right here.
Even if there was such number, including 5, 1, 5, 0.
Yeah.
I don't expect it to be small, right?
Yeah, again, I would use the same argument to say that.
It's small, but different things.
Yeah, no, but here this is more important. This guys are going in the opposite direction. But here actually we see that.
Yeah,
here
I think it's static here.
right, yeah, 5 is static. So at least initially it plays a role.
From the perspective of the normalization group, you have two different dynamical exponents. that usually happens if one equation is completely dependent.
Okay. But it, but it's, I mean, even if it's not independent, like it's still possible that
If all of the couplings are irrelevant.
irrelevant, right? Yeah. So the one is arguing that they are irrelevant. Okay. Okay, so I think that's maybe now we should move to speed change, the overview of putting hydrodynamics or dynamic change. And now basically we see that speed change are more or less examples of are more or less the thing that we can have with change, oscillator change. So now the first example I'll talk about is the rotor change. Okay, this is not a thing, but kind of, and so it's okay, so basically I have a sort of angle things moving in a plane. Speed of and so there's an angular momentum here, and then some traction which tries to align all the rotors. Okay, so now if we so I mean, so this model was again studied in the context of heat conduction, and sort of the surprise was that okay, so this looks at first glance more or less like the so I mean so in general I have written some general interaction for anharmonic chains. Okay, and this looks more or less like another anharmonic chain. But this model, so again, people studied heat conduction in this chain, and what was surprising is that this actually gave Fourier's law satisfied. So shows. Again, I mean the momentum, and these are both conserved, right? So it seems to have the same conservation laws, but still it has normal diffusive transport. There's no anomalous transport. Okay, so now the reason for this is basically okay. So if we is the fact that phi is an angular variable. So it's phi is defined 0 to pi. Okay, so now which means that it's no longer so earlier we had identified three conserved quantities. One of them was the volume of stretch, which is given by, which in this case it would be 5 plus 1 minus 5. But now this is I mean these angles are whenever they cross pi, I mean this jumps randomly. So it's I mean we can't really specify the value of Rx, right? So it's not a valid conserved variable. So we have just two conservation laws in this system. So now we can again try to do the derived hydrodynamics, but with two conserved quantities. So this was not a valid.
So,
Yeah.
yeah, how do they know how many conservation laws are there? That was general prescription, right?
No, okay. So if you're and typically you expect like only energy and momentum should be, these are obvious conserved quantities. Now, if they're integrable,
Or the straits here, I mean, you have to know that you are looking for some detection.
no, so stage is, I mean, and, like in a fluid, and stage just corresponds to number conservation. So that is also a sort of obvious conserved quantity. In this case, it's a bit subtle and it looks like a conserved quantity because if I just take Rx dot, it's still, if I sum it up, it's still 0. It looks like, but then these are doing these jumps between pi. Right? So because of that, it's not a conserved quantity. But otherwise, of course, I mean, it might be an integrable system, which is right, yeah. But otherwise, typically, I mean, that these 3 should be the. So this is not valid. So then we just write the equation for momentum and ds. In this case, Vx dot is this looks from so again, if I write equations of motion, then I get this sort of continuity equations where this pressure is just minus of from the equations of motion is just minus time. Okay, so now, so again, now I have to compute the expectation values in the local Gibbs state, and so I have to say what is the Gibbs state. So in this case, the Gibbs state does not need the stretch variable; it's only specified by the angular momentum and energy. So the local equilibrium state, which is the function of all these Rx and Px, is given by okay, so I can specify the momentum and I can specify the temperature, but I don't put a pressure term that in the Gibbs state. Okay, so this is the big difference, and this makes all the difference. And then I have some finalization. Okay, so now with this Gibbs state, if I find the expectation value of these currents, then it's clear that they vanish identically. So the currents. Okay, so which means that in my when I write my hydrodynamic equations for these two fields, what oh, so omega is the like in the I put an average earlier I was putting an average momentum, right? Like U field. So this is now is like an angular momentum. That's the, so the two fields are now in omega is a function of XP and energy is a function of XP. These are the hydrodynamic after posting.
So your P doesn't depend on omega.
P average is omega. I mean,
You have a big P.
oh, it's big P is the pressure, but big P is big P doesn't depend on pressure, right? Yeah. I mean, so no, see, big P is sorry, P was this was an operator which is just minus sign RX. So that was the microscopic definition. It's just this.
Yeah.
Now I take an expectation in this Gibbs state, right? And this will just vanish because it's an odd function and it's an even function. So it just vanishes. And similarly, if I take expectation of this, then it's just product, and this is already 0. So both of them vanish. Right. So the currents are all currents are identically 0.
Okay, fine. So when you do your average over state, which basically as is, you fix omega.
Yeah. It's fixed, right? Yeah.
And then you do an average for given fixed omega.
Right. Yeah. So at this level, like omega is not a function of x and t, right?
Yes.
It's just some constant omega. Okay, so now in this case, therefore, my equations are so I have this C of omega and E, and there's no other term. So all I can have is the diffusion term. Okay. So so in this case, it turns out that and the diffusion also one can argue that there are no cross terms, and it just looks like. And then we can have noise terms. Okay, so these are these are diffusive, completely diffusive fields. So both momentum and energy are diffused. There are no propagating sound. Okay. Okay, and this, I mean, I'll show again data from simulations where you can see this very clearly. But,
So there's a after the matrix, and then the B matrix is the same thing that we had earlier, or that's B sub X.
sorry, so earlier I had a matrix, right?
Yeah.
Now I'm saying so of course this depends on the field, so this is d omega and this is d omega. And I'm saying the off-diagonals, in this case, one can argue that they vanish because of different symmetries of the two currents. Okay, so now we'll go to the same system. If we look at very low temperatures, then one expects something different to happen, because at very low temperature, at 0 temperature, for example, the spins would all be aligned. And if it's very low temperatures, we can imagine that there are small fluctuations around the sort of an ordered phase. Right? So this is 1D, of course, there's no true broken symmetry. But let's say, I mean, if we are really very low temperatures, then effectively it might look like you are in broken symmetry phase. Okay. So now let's look at that case then.
Here we don't have any spinoid bone. We don't have any spinoid bone. That's pretty fast. No energy execution. Yeah, I mean just spinoid. Just spinoid.
Spins, okay, because these are yeah, you could have spin waves. Right, yeah. But I mean, but once at low temperature, we'll see basically that probably spin waves at and they will give rise to, of course, sound mode. Right, spin waves. Right, yeah. Yeah, it's like sound waves. I mean, okay, so Okay, so on the screens almost aligned, so we expect small fluctuations about an ordered state with our about our X. And so if we are more or less confined at this, small Rx, then okay, so we okay, so we had the potential which looked like so our potential was minus G cos of Rx. It's like so this is the potential. Now, at very low temperatures, we are more or less confined here. And so we might as well replace this potential by something which, so this is minus pi pi. Let's say which goes up to infinity at minus pi and pi. So then we are more or less in the situation of the earlier anamorphic states, right? And then there's no difference once you do that.
And the stretch becomes again the conserved quantity.
Exactly. Yeah. So then now stretch is a conserved quantity, and we can just do everything like what we did before. And now, once you introduce stretch, you can introduce the pressure term in the Gibbs measure, right? And so then the currents will again now be automatically non-zero. Okay. And so then we can just do the analysis of the usual NR, and we'll have Euler terms and so on. And so in this case, again, the now prediction will be that there are sound modes and weak mode. And in this case, it's clear that okay, so it's potentially even, of course, and finally get interest in zero pressure, right? So we'll get actually this diffusive and this leading.
So as you increase the temperature, you have a transition or a crossover from.
It's a crossover.
To,
Right, yeah. So here, I mean, if you really take a large system at very low temperatures, you will see, so this, at very long times, this will actually, you will see that this decays exponentially. Right, and so basically it depends on.
slow down, you go diffuse.
Yeah, it will slow. No, so this will become diffusive. This ones will just vanish, right? I mean, there's no sound source, and
So does it, so when you say it reduces to the harmonic chain, does it reduce to it with arbitrary alpha, both alpha and beta non-zero, or does it, some of, or
it's an even potential, right?
even
So
alpha
alpha
is
is zero.
it's alpha is
Alpha is
zero,
zero, right.
exactly. So it's only beta.
Right, yeah, right. Yeah. And yeah, in fact, if you expand this,
So when alpha before, and then when alpha was zero and you'll have only beta, does it, what difference does it make?
so I said like pressure, like there was these two cases, right? In one case, if alpha is zero, then and pressure is zero. This is the case that will be relevant in this case.
Yeah.
Then the heat peaks continue to be diffusive, while the sound peak is still steady, but with a different exponent. Okay, so right. Okay, so this is what is the prediction, and so this is in this case we get maybe sorry, this is and like from the microscopic theory, we know exactly like what are the sound speeds and what are the exponents and so on. So that's, there's a complete prediction. Okay, so so I mean, so now we'll go to really the Heisenberg spin chain, where again we'll see something very similar. Like at low temperatures, you expect again like some ordered phase, and high temp, yeah. In that case,
As you go.
at low temperature.
Yes.
So low temperature again, so at high temperature you expect Fourier class, and at low temperatures you expect that J should you should get 1 by n half. Okay, and if you do a simulation, what you would see is, I don't know if they saw the crossover, but like Shota said, and if you are at really low temperatures for a long time, you should see this power in half. But then if you go to longer times, then it's because it's not exactly conserved, you will again go back to the Fourier. I think this has been seen in simulation. Like eventually you'll always solve it. It's diffusing. Okay. Right, okay, let me just introduce the Heisenberg. Okay, so now we put a slightly different model. So now let's so so this is this anisotropy, and we'll mostly be interested in the case delta less than 1. So this is called the easy plane case. So if I am at very low temperatures, or let's say the lowest energy configuration state for this system at when delta is less than 1 is that the spins align in the XY plane. Okay. If delta is greater than 1, the lowest energy configuration is it aligns in the along the z axis. But in this case, it aligns in the XY plane, and so it's called easy plane. This is what we'll be mostly interested in. Okay, so now here, what is the dynamics? So the dynamics is just x bar dot equals to x bar dot, where Bx bar is just the local field at the site x. So this is the dynamics. And now what we do is you can cast this dynamics in exactly a Hamiltonian form. This is already in Hamiltonian form, but a more see here we see that it has 3 degrees of freedom, right? So it looks like it's not really Hamiltonian, but because Fx square is equal to 1, so we can write it has really 2 degrees of freedom at each side, and supposing we write Fx square is equal to and then we call this this region cos of theta x. We call it so the z component of the spin. We call it s of x, and so there are only 2 variables now: phi of x and s of x. So this is now, and this Hamiltonian I can express in terms of this Sx variables, and one can see that this is completely equivalent to saying that phi star So this has exactly the Sx phi x and Sx are like momentum and position and momentum, and it has the usual Hamiltonian structure. But of course, the Hamiltonian is all mixed up. It's not dx squared plus something. It has complicated structure. Okay, so from this now we have to. So what are the conserved quantities? So let me just say what are the conserved quantities and I'll start. So typically this is supposed to be a non-integrable model. So the only conserved quantities are energy and of course the Z component of nitration. So the F of X and the energy.
And that you would do by taking the moisture.
Yes, so I mean, if energy is of course obviously and effects, if I just take let's say GDP or let's say this from the equations of motion I can say that it vanished. Yeah. Okay. So these are the obvious conserved quantities. So first we will then show that if these are the only conserved quantities, then again you get only the prediction is that the Euler currents vanish identically and you get diffusive transport. But at low temperatures, again you have an so then the system aligns in the XY plane and you have small fluctuations and there's an extra conserved variable. Okay, and then you again have a similar situation and we get all sorts of interesting anomalous behavior. Okay, so I should say that what I am saying is actually, for example, if we look at tracking the densities with chapter 8 is on hydrodynamics. No, it's chapter 8 is hydrodynamics. Chapter 6, oh right, yeah. But here chapter 8.2 is on rotors and chapter 8.3 is on spin chains. And they also discuss the broken symmetry phase. But I think what was not maybe what is new is that the fact that this nonlinearity can lead to this sort of non-trivial anomalous features. So that is the sort of thing that.
They did not study on the.
Right, yeah. I mean, so I think they stopped at linear and at least the discussion in those. So here there's some new insights on okay. So,
Any virtual comments? So, in this lecture, you're sticking to the kind of Hamiltonian dynamics, which is coming from this potential. So then you get kind of reciprocal type of equation.
yeah. Oh, okay.
Think of
Non-reciprocal interactions. Yes, so finally, of course, the conservation laws are important, right? So as long as you know what are the conserved quantities or the slow fields, then you can still do this. Okay, and then of course the other thing that we use very much is the idea of local equilibrium, right? Which is also not clear. Okay, but you could still use local equilibrium in the sense of like you have some steady state, and maybe the local steady state is that's what varies slowly. So I think one can still apply this.
Quantum models.
Right. Yeah. So quantum, of course. No, okay. So there, of course, there is a lot of. I will talk a bit about like if you take quantum xd, and if you take the same system, it's integral. So it has the infinite number of conserved quantities, and there again you get KPZ for completely different reasons. Which okay, it's not completely understood, but you still get spin-spin correlations are KPZ. Sorry, delta equal to 1. Sorry. For delta equal to 1, you get yeah. Which is not, I think, completely understood. And yeah, that's true. Even in the classical, if you take an integral model, you again get.
Something, yeah. What happens when you take the three classical limit? No, as you said, quantum version is integral, the classical version is not integral.
Yeah, so.
Yeah.
What
What happens?
But you can't take, I mean, of course, then you have to take large S, right? So this is spin half. Spin half is, so you can't take the. If you take large S, then it's not integral.
Abhishek, you have mentioned that there was some model in which the one of the eigenvalues is not zero, right? The zero eigenvalue also becomes non-zero in the A matrix. So the A matrix usually has a zero eigenvalue.
Oh, right, yeah.
But you said you have some, there's a model in which it becomes, even that becomes non-zero.
There are no zero.
No zero eigenvalue.
So,
So which was this one?
I know this I have to check, and I don't remember. But no, what I was saying is that this Cn minus min need not be equal.
Okay, but
But like, if, for example, if there are two more, like there are the systems with two, there's two fields.
right,
One of them like 6 and the other modes,
right.
and that is one, that is there.
No, but can you have a situation where you have three modes?
Yeah.
And all of them have non-zero
Different
speeds,
Different speed.
different speed and non-zero speed.
This one could, but I right now I don't.
Most
Not
of the-
in this kind of systems, and like typically you expect there should be a bit more.
Right, and most of these examples, we only have, we definitely have 1 0
Right, yeah.
speed, right? So how do you?
Yeah. Because physically you expect it, there should be a
Exactly.
bit more visible properly.
Exactly. So is there any way, or is there some constraint which forbids it from having?
Yeah, actually, I don't know how, like from the A matrix structure,
Right,
is it obvious that there should always be a zero mode? Yeah, that's
Yeah.
not
That's not-
obvious that there should be a zero. I think but maybe there's some symmetry which says.
But the different velocities and time diversion symmetry in order to be there. That's why I thought you get a CN minus C.
But yeah. Yeah, I'm not sure.
For the quantum, so the speech and hydrogen approach are in very different areas.
Yeah.
But for the, you could also consider the quantum rotor, like, very, that is also, that I guess is not.
Quantum rotor.
You could try quantum rotor models and then write on the.
Right, yeah. Then if it's you expect it to be non-integrable. Right, yeah, then of course you will get diffusive. I mean, typically if it's non-integrable, you will get diffusive
Well, one
hydrodynamics.
thing that you develop the hydrodynamic theory.
Yeah.
I mean, if then quantum nature comes in.
Oh, that is, yeah, that's a very interesting question. I mean, see, finally in the hydrodynamics, at the Euler level, you just get equations of states. That of course comes, is determined by whether the system is quantum or particular. That's one level. But in the transport coefficients, I don't know.
I don't know.
Yeah, I mean, if we just use Green-Pogogen, there will be some, but I don't know if there's any like qualitative difference. That is the, yeah, I'm not sure. Otherwise, it looks, hydrodynamics should be more or less same for.
Other question? No, let's start.